Hello, I'm Wissam Sam and I'm modeling engineer at Amcan Engineering. I will introduce our new software Vision, which is an advanced modeling tool for RF and microwave system simulation. In this context of complex RF and microwave system design, system designers are faced with different challenges such as 5G with very wideband signals and also complex architectures such as active antennas with a large number of circuits. To evaluate and validate the system specification as a whole, the current strategy is to use a data flow simulation that requires behavioral models of different RF circuits. Our solutions helps you to create your behavioral models that take into account different phenomena, for example, linearity or memory effects. Thereby, our solutions bridge the gap between baseband and RF design and improve co-simulation and co-design process. Our goal is to strengthen, accelerate, and secure your system design flow with a turnkey circuit and system level modeling environment. With Vision, you can control a measurement bench for model extraction and validation. Vision is also composed of a circuit model toolbox to extract behavior model of active and passive circuits. As well, we provide system-level macro modeling solutions and direct export functionalities to the main commercial system simulators like VSS. The unique features are bottom-up multiple-level hierarchy model for data flow simulation. Behavioral models are taking into account nonlinear load mismatch effects, in-band and low-frequency memory effects. In the modeling of your system, you can include mixer or frequency converter. The main goal is to provide you accurate models, speed your simulation, and have a user-friendly environment. The architecture of the solution. The Vision platform starts with the modeling instrumentation. You can control your measurement bench to capture the different phenomena that appear in your device, like high and low frequency memory effects. With this data, you can extract your behavior model of different circuits thanks to device modeler. In System Modeler, you can build a schematic of your system, simulate it with complex signals, and validate the design of your system. Finally, you can export the macro model of your system with a solver to a data flow system simulator like VSS. Another way is to start with a commercial circuit simulator. If you have the RF design of your circuit, we provide templates to extract this data to build your behavior model. The rest of the methodology remains the same. There is also a model verification test bench to compare your physical system with the Vision macro model, and so to qualify your modeling process. I will now go into more details in the modeling process, starting with the measurement bench. This is a bench control for model extraction. There is a demonstration in our booth. Here, Vision controls the vector signal generator and a two-port vector network analyzer with access to the receivers. We characterize the power amplifier to catch high-frequency memory effects thanks to power and frequency sweep of the CW signal. With a 3-tone signal, we can catch low-frequency memory effects for different input power of the center frequency and different frequency spacing. With a tuner, you can build a bilateral model to take into account the output mismatch. There is also a bench control for model qualification if you want to test your system with modulated signals, pulse or two-tone signals, so you can measure figure of merits like ACPR or AM3. In Device Modeler, you can build your library of components such as power amplifier, low noise amplifier, mixers, and filters. And for each circuit, there is a user-friendly interface to tune your behavior model with a few number of parameters. There is also a test plan to validate your model with other signals. Thereby, you can check if your model shows a physical behavior. After the extraction of the model, you can directly see the comparison of characteristic curves between model and measurement data. If the model is not accurate enough over the entire power range and frequency bandwidth, another extraction can be done by changing the value of parameters until a satisfactory result. In System Modeler, you can create the schematic of your system by using the different models extracted in the device modeler part. You can submit your modulated system to different signals such as pulse, two-tones, or modulated signal. Here, I wish to present you an example of application of this methodology on the design of a tone converter. It's a down converter from 3 GHz to 1.28 GHz with a mean input power of minus 25 dBm. We will go through the following steps: extract a model for each circuit thanks to device modeler, create the schematic of the down converter, simulate the modulated system, and compare with the measurement data. The first component is the LNA that exhibits memory effects. The first graph shows AM/AM curves for different frequencies. This dispersion is called the high memory effect, and the model perfectly reproduces the measurement. The second graph shows the variation of the AM3 as a function of the two-tone spacing for different input power. These measurements in red allow to capture low-frequency memory effect. There is a good agreement between the model and the measurement. The measurement of the first two graphs are part of the data needed to extract the model. Now the last graph is used to validate the model on a different signal. It shows the comparison of the measurement and the model on a pulse at 1 dB compression gain and confirms the good representation of the memory effect. The second circuit is a bandpass filter. As the models are used in a transient simulation, it is necessary to create a behavior model in time domain from S parameters data built in the frequency domain. The second amplifier doesn't exhibit low frequency memory effects. The model will only take into account high frequency memory effects, and it consists of approximating AM/AM and AM/PM measurements at several frequencies. We observe an excellent approximation by the model. The advantage is to be able to use the most suitable model and not oversize the measurement bench. We provide a model of mixer that takes into account the non-linearity and the high frequency memory effects between the RF and EF band for a fixed LO power level. Finally, I show you an example of a behavior model that takes into account the mismatch. For that, we measure the gain for different frequencies and gamma load presented at the output of the amplifier. In System Modeler, you can build a schematic of your system. We present here the different blocks that can be found in the Schematic Editor. We find the different models corresponding to the elements of the system. The Schematic Editor provides some probes to see data at different points of the system. The data collected by these probes are useful for displaying the different figures of merits. Sources are available to test your system model against simple signals such as two-tone or pulse signal. You can also add your own signal in IQ file. Here we compare the simulation of the modeled system and the measurement on the pulse. We have excellent results before the mixer and also at the end of the system. Here we use a 256 QAM signal at 1 megasample per second. The graph shows a waveform at linear operation, and there is a good agreement between model and data. And we have also good results at 1 dB compression gain. We calculated the gain in the main channel, and the comparison show an error less than 0.4 dB. We measured left and right ACPR and observe excellent results in the gain compression. Now we change the sample rate of the signal at 20 megasample per second. Memory effects in the system start to be excited. The display of the waveform shows good results at linear operation and at 1 dB gain compression. The comparison of the gain in the main channel shows an error less than 0.6 dB. The simulation results at the right and left ACPR are in agreement with the measurement at this sample rate. We did the same exercise by going to the limit of the measurement bench with the sample rates of the signal at 42 megasample per second. The error is less than 0.7 dB on the gain of the main channel. And at this sample rate, the modeled system shows good prediction on the left and right ACPR. You can export your model to VSS. We have created a library in VSS that includes 5 fixed topologies. They are differentiated by the number of input and output ports. It's simple to use. You drag and drop the vision macro model on the system level design with the data flow simulation. The vision macro model contains the schematic of your system and the vision solver that takes into account the mismatch. Here we show that we get the same results in Vision software and VSS, so you can use both Vision behavioral models and all VSS capabilities to get the most out of your RF systems.